Alright, let's start with page 109. And this is your homework right here for this section. On page 109 we have a definition of an informal definition of a limit. Okay, let me describe to you what that means. They tell you that limit, and this is how you read it, as x goes to a, f of x is equal to L. Okay, what that means is, as x approaches a, limit of the function goes to L. So let's draw a little picture. And let's say we have a function, we call this f of x. That's my y-axis and that's my x-axis. And let's say we have some value here on the x-axis, we call that a. And let's say if you plug into the function, if you get f of a, and we call that one L, same as L. So what they're telling us is, as x goes to a, so that means when I come from the left and when I come from the right of a, the values of the function get closer and closer to f of a, okay, as I get closer to a, and then both from the left side and the right side, the value of the function gets closer and closer to f of a. When that happens, okay, I have a limit of a function that's equal to L. Now, it doesn't necessarily mean that you have to, the function has to be continuous. It could be discontinuous. So let's take a picture of a discontinuous function. And let's say that that's my a. And of course, let's say that is my L. So, as I get closer and closer to a from the left side and the right side, look at the graph. Okay, the value of the y gets closer and closer to L from the both and the left side. So the limit still exists. This still applies even though f of a is not equal to L. Okay? Alright. So that is the first definition, page 109. So let's take a look at an example. They give us an example. Let's still go to page 110 and let's look at an example 2. So this is page 110 and this is example 2. And they say limit as x goes to x over square root of x plus 1 minus 1. Okay, they want us to find what this is equal to. Well, as x goes to 0. Okay, well, if you actually put in 0 on top and put 0 on the bottom, okay, you're going to get 0 over 0, which is undefined. Okay, so it's in determinate form. So you really can't say it's equal to 0, okay, or undefined. So you have to figure out what actually happens to the limit. So even though you don't have a value there at 0 is equal to 0. So let's take, as x goes to 0, we don't have a value of x. Okay, let's take, let's use graphing calculator. And let's go over here and let's clear that. Clear what I have here. And let's punch in our function. Okay, so punch in x and divide that by parentheses. We have rad x plus 1. So x plus 1 close parentheses. And then I have a minus 1 close parentheses. Let's put that in there. Yep, that's what the function is. And what we're going to do is we're going to create a table. And that's what they have in the book on page 111. They have a table for you. So if I'm going to create the same thing here. We can do this. And I'm going to go to what's called the table set. Okay, so which is F4. So second table set. And I want table start to be at 0. Okay, enter. then I'm going to go down, and I want to, it looks like they're going, what, 100, so 0.01, okay, let's do that. Okay, enter again. Now let's take a look at our table. So that's at 5. So table. Right. So clearly, now here's my x values on the left hand side and my y values on the right hand side. So as I come from the left hand side of 0, negative 0.03, negative 0.02, negative 0.01, okay, I'm getting closer to 2 on the y value. Okay, and of course that 0 itself is undefined. Now let's look at coming from the positive side. Okay, 0.04, 0.03, 0.01, I'm getting closer to 2. So even the function is undefined, okay, at x is equal to 0, but we see the function is going to 2, so we say limit of this function is 2. Okay, limit of this function is 2. Okay, that's what you see on the table. Okay, let's take another look at let's take example number 3. Okay, and that is limit as x goes to 0, sine of x over x. Obviously, you can't put in 0, so we will have to define this using a table. So let's go back to the function and let's clear that one out. And I want to punch in sine of x over x, so have a sine of x, parentheses, divide by x, enter. Okay, I have that, and I'm going to 0. Now what I want to do is I want to make sure everything is in radians, so I'm going to go to mode, make sure I'm not in degrees, and if you look here in the mode, I'm in radians, so I'm good to go. Okay, and then I'm going to get table set again. Table set. Where do I want to start that? If you look at the table that is given to us on page 111, it looks like I'm going 1/10, okay, from both the plus and the minus. So let's change that to table start 0 is fine, okay, and I have 100, so let's go to 1/10. So 0.1. Okay, enter, and enter again, it will save it, otherwise it won't save it. You have to enter twice. Okay, so again, at 0 the function is undefined. Okay, let's take a look at from the both sides. From a negative side, it's going to 0.9933 to 0.9983. On the right hand side, you're getting the same thing. So it looks like it's going to 1. So the limit of that is 1. Both from the left and right hand side is going to 1. And that's what the table shows us right there. And they did the table for us in that page. And then let's take a look at page 112. They give us another example. Okay, they give us actually a graph of a function that looks like this. F of x is equal to absolute value of x over x. And we know this is really two functions in one. Okay, so this can be written as, okay, positive 1 when x is greater than 0, and negative 1 when x is less than 0. And we had this, we worked with this before. Okay, so if we were to graph this function, it will look like this. It can't be 0, so it's going to look like that to the right of 0, and then to the left of 0 is going to look like that. There's my y-axis, and there's my x-axis. Okay, now what happens when you get a function like this? Well, when I come from the right-hand side, limit of this function goes to, this is 1, and this is negative 1. So this is called a one-side limit. So limit as x goes to 1 from the right-hand side, okay, of absolute value of x over x, that ends up being 1. Okay, but when you come from the left-hand side, okay, the curve is going to negative 1. So limit, I write limit as x goes to 1 from the left-hand side, absolute value of x over x is equal to negative 1. Well, these two values are not the same, but they have to be if the limit exists. So we say limit does not exist, D&E. Okay, limit has to go to the same value. Okay, it doesn't have to be defined there, but it does have to go to the same value from the right, both from the right and from the left. Okay, so these are known as one-sided limits, from left-hand side and right-hand side. Okay, this is the right-hand side. Means from the positive side. This is the left-hand side. From the negative side. All right, and then if we hop, skip, and jump, go to page 113. That gives us a couple more definitions. Let's take a look at the most important one is this one. Okay, I'm on page 113. We look at definition 2.13. Okay, it says limit. This is very important. Limit as x goes to a of f of x is equal to L if and only if. Okay, and we write two f's with if and only if. Okay, if and only if limit as x goes to a from the left side of f of x is equal to L, and limit as x goes to a from the right side of x is also equal to the same L. Okay, that has to be true. Okay, otherwise limit does not exist. And they give you, in example 4, they give you some pictures on page 113. Okay, where limit does not exist because both from left and right hand side goes to different places. Okay, I want to skip to page 114. Okay, so page 114, they give us a graph that looks like this, an open circle here and there. Okay, and they ask us, they tell us this is your f of x function, and they tell you a is right there. And they ask you this question, does the limit exist? Yeah, limit does exist. So when I go from left of a, and that is limit as x goes to a from the left side of f of x, okay, is equal to, and of course they give you 2 right there, so it's equal to 2. And what about when I come from right side? When I come from right side, my value of the function is getting closer to 2 also. So limit as x goes to a from the right of f of x is equal to 2. Because they match up, then therefore I can say limit as x goes to a of f of x exists, and that's equal to 2. Okay, they give you another picture where they put a little dot on above that. That's okay, because here, let's say this value is 3. Okay, even though f of a is equal to 3, it doesn't matter. This does not matter because this is still true. Okay, that dot could be anywhere. It could be above it, could be below it, or it could even be closed off. And now, let's say we didn't have that, so let me erase that. Okay, let's say we didn't have that. Now, we do know that f of a is equal to 2. That's okay. Okay, and the limit still exists because both the left hand and right hand side goes the same value. Okay, and then they talk about vertical asymptotes, and they find vertical asymptotes in the bottom of page 114, page 114. So let's take a look at a graph that looks like this. Okay. Alright, let's call this function f of x, and this is my x-axis and y-axis, 0, so on and so forth. Okay, now let's find a limit. Limit as x goes to 0 from the left-hand side, f of x. It's going down, so it's going to negative infinity. Okay, and then limit as x goes to 0 from the positive side of f of x. It's going to positive infinity. Okay, so first of all, okay, when it goes to positive infinity, this is where you have vertical asymptotes. So vertical asymptotes, okay, exists when this happens, when the function shoots down or shoots up. Now, limit does not exist here. Okay, so limit does not exist. You can write D and E. Okay, limit does not exist because infinity is not a limit. So vertical asymptote is defined when the curve goes to positive infinity. And of course, in the following page, okay, page 115, they give you the definition of infinite limit. Okay, increasing, decreasing with the bound, and these are known as vertical asymptotes. Now you can have vertical asymptotes with all kinds of curves. So you could have vertical asymptotes when the curve does this, and they give you pictures of that. Okay, in this one, if you call that one, okay, limit as x goes to, let's say, 0, okay, from the left-hand side, f of x, obviously it's going up, the curve is going up, so it's going to go to positive infinity. Limit as x goes to 0 from the right-hand side of f of x, okay, that means when you come from the right, it's going up also. Okay, it's going to positive infinity. Even though they're both going to positive infinity, okay, limit still does not exist. Okay, we have to say limit does not exist. But sometimes on multiple choice question, we're checking for a behavior of a function. We can still write the behavior of the function limit as x goes to 0 of f of x is equal to positive infinity. Which just basically tells us even though limit does not exist, the curve is going up both from the left and the right of 0. Okay. Alright. Now if you turn to page 116, page 116, okay, and they give us a definition, 2.15, okay, and they define a vertical asymptote. Vertical asymptote occurs when f of x either goes to positive infinity or f of x either goes to negative infinity as, okay, negative infinity as, okay, x approaches a. It doesn't have to, it could be from one side or both sides. Okay, and that's the definition of vertical asymptotes. Of course, they give us an informal view of a horizontal asymptote also, so let's keep on going, and which is on page 117. Okay, so page 117, okay, there's another definition, which is 2.1.6. Okay, that's the definition of 2.1.6, and that tells us, that defines as what horizontal asymptote is. So when you see limit as x goes to positive infinity of f of x is equal to some number L, okay, then this defines a horizontal asymptote. But of course, we also have to check from the left-hand side. We'll do that in a second. So let's just draw a picture of what this is. That means that let's say you have a graph, and let's say we call that L. Okay, and we have, and that is your L. Let's say our curve does this. Okay, so clearly you can see as you go to positive infinity, this curve is flattening out, okay, against L. Okay, so that means this means that you have a horizontal asymptote at L. So let's actually put some numbers in. Let's say limit as x goes to positive infinity of f of x is equal to 5. So the graph of that function will look something like this. Call that 5. Okay, draw a dotted line. And let's say if a curve does that, as you can see, when I go to the right, okay, the curve is getting closer to 5. So that means we can say we have a horizontal asymptote, okay, when that occurs at y is equal to 5. So horizontal asymptotes are end behavior. We're checking for end behavior. E-H-A-V-I-O-R. End behavior. Okay? That's what horizontal asymptotes are. Checking for end behavior. Now, you can also have curves with horizontal asymptotes that you could have a curve that does this. So when you come from the right, it could do that, okay? And then when you go to the left, it could do that. So in this particular curve, okay, let's call that y, call that x. In this particular curve here, Okay, limit as x goes to positive infinity of f of x is equal to 0. Okay, and then limit as x goes to negative infinity of f of x is equal to 0 because it flattens out against 0. So it has a horizontal asymptote there. Now, it doesn't have to be the same value. Okay, so you could have a curve. Let's draw a curve where it goes to two different values. Okay, so let's say when you have a curve here, if you remember the tan inverse. Okay, the tan inverse does that. Okay, and that's pi over 2, and this negative pi over 2, you have a horizontal asymptote there. So limit as x goes to positive infinity of tan inverse, okay, of x is equal to pi over 2. Okay, but limit as x goes to negative infinity of tan inverse of x is equal to negative pi over 2. Okay, that means it has two horizontal asymptotes when you check the end behavior. As you go, end behavior means when you go all the way to the right, all the way to the left. Okay, so you have one horizontal asymptote at y is equal to pi over 2. You have another one at y is equal to negative pi over 2. It doesn't have to be the same from both when you go to both left and right. Now, the other thing you need to know about horizontal asymptotes before we go on doing some problems is this, that just because you can have a curve like this, okay, let's say we have a curve that comes up and it gets closer and closer and closer and closer and closer to 0. Okay, so as you go to the end, okay, let's call this one our f of x. That's my x and that's my y. Okay, now limit as x goes to positive infinity of f of x is equal to 0. So I have a horizontal asymptote at y is equal to 0. Even though the curve crosses the x-axis, it eventually flattens out on the x-axis. So end behavior means what happens when you go all the way out to the right. So a curve can cross horizontal asymptote, but a curve can never cross a vertical asymptote. Okay, so a curve can cross horizontal asymptotes many times. So there's nothing wrong with that. Okay, horizontal asymptotes refers to end behavior. End behavior. Okay, so let's take a look at some of the even problems. Let's start with page 118. Okay, this is problem number 2, and let's take a look at the picture of that. Okay, and you can, if you have your book in front of you, and you need to have your book in front of you, okay, it's going to go much easier for you to figure out what I'm talking about. So this is at 2. Okay, line like that, and then close circle there, and this flattens out at 0. Okay, now we're going to answer all the questions based on this curve. The first question, A, they want you to find the limit as x goes to 2 from the left-hand side of f of x. Okay, so when I come from the left-hand side, as I get closer and closer to, this thing is going to 2. Okay, B, limit as x goes to 2 from the right-hand side of f of x. That means I'm coming from the right, I'm going to 2. As x gets closer and closer to 2, the value of the function is getting closer and closer to 0. So that's 0. Look, these two do not match up. So what can I say in part C? Limit as x goes to 2 of f of x, okay, does not exist because they have to match up. All right, but in part D, what is f of 2? F of 2 is actually 2. So that's where I have a closed circle. I have a 2. In part E, I'm checking the end behavior as x goes to negative infinity of f of x. Okay, that means when I go to far left, it's going to go to 0. Okay, and then finally f which is limit as x goes to positive infinity of f of x. So when I go to the far right, okay, it's flattening out against 2. So it does have a horizontal asymptote 1 at 0. I have another horizontal asymptote where y is equal to 2. Okay, that's problem number 2. So now let's go to problem number 4. I'm on page 119. Okay, problem number 4. Okay, they give us the Wolverine curve here. Okay, so let's take a look at that. So it looks like this, something like that. Okay, and they call this g of x. Alright, they do give us some values, so that's, let me say that's 5 and negative 5, that's 0. Okay, so let's see what they ask us. In part A, they want us to find limit as x goes to 0 from the left-hand side of g of x. So I'm coming from the left. Okay, the value of the function is getting closer to 4. Okay, B, limit as x goes to 0 from the right-hand side of g of x. So when I come from the right, again, the value of the function is going to 4. Oh, they match up this time. If they match up, that means in part C, limit as x goes to 0 of g of x is equal to 4. They have to match up for this to be true. And then in D, what they ask us, they say they want us to find what is f of g of 0. And g of 0 is 4. And then in part E, okay, they want us to find the end behavior. Limit as x goes to negative infinity of f of x. That means as I go to the left, the curve is going up. So that means it's going to go to positive infinity. That means it has no horizontal asymptote. And then f, limit as x goes to positive infinity of f of x. So when I go to the right, the curve is going up, so it's going positive infinity. So I have no horizontal asymptote there either. Okay, so let's go to example number 6. Problem number 6, sorry. So problem number 6, I'm on page 119. Take a look at that picture, and I'll draw it for you. I can draw the grid for you, so I'll help you to take a look at the picture. I have a hole here, I have a line, and that's my 3. And then as I go up, I got a closed circle up on top, and that's my 3. And it's my y-axis and my x-axis, and this function, they call this big f of x. Okay, part A. Limit as x goes to 3 from the left-hand side of f of x. So as I go from the left-hand side, and they do give me a value for this, and that's 2. As I go from the left-hand side, the value of the function is getting closer to 2. And then B, limit as I go to 3 from the right-hand side, what's happening to the value of the function? When I come from right-hand side of 3, it's getting closer to 2. Okay, C, I can say, since these two match up, and they have to match up, as x goes to 3 of f of x, that's equal to 2. What about D? What is f of 3? Well, it's not 2, because it jumps right there, and f of 3 is 3. And let's check the end behavior. Okay, that's my E. Limit as x goes to, that one is negative infinity of f of x. When I go to the left, it's going down, so therefore it goes to negative infinity. That means no horizontal asymptote. And then f, limit as x goes to positive infinity of f of x. So that means when I go to the right, the curve is going up. Okay, that means it has no horizontal asymptote. Okay, so now let's go to problem number 12. So a couple more problems. Okay, so this is number 12. Okay, I'm on page 119. Okay, they give us a picture of a curve that looks something like this. Okay, this goes up and down. x-axis, and that's my y-axis. And this is, we call that g of x, the function g of x. A, limit as x goes to 0 from the left-hand side, there's my 0, okay, of g of x. So when I come from left-hand side, the curve is getting closer and closer to 0, so that's 0. And then part B, limit as x goes to 0 from the right-hand side. When I come from the right-hand side, the function is getting closer and closer to 0 also. Therefore, since these two match up, okay, then I can say C, limit as x goes to 0 of g of x is equal to 0. And in part D, g of 0 is 0. Okay, the actual value of the function is 0 there. And then part E, limit as x goes to negative infinity of g of x. Okay, so when I go to the end behavior, this is just on the left-hand side. This thing is just going up and down. So it's not going to any particular value. It's going up and down. So therefore, limit does not exist. And then finally F, limit as x goes to positive infinity of g of x. Well, if you look at that, when I go to the right over here, it's getting closer, the curve is getting closer and closer to the x-axis, and it's getting closer and closer to 0. So limit does exist. So this one has a horizontal asymptote at y is equal to 0. Y is equal to 0. That's my horizontal asymptote, because it does go to a value. Okay. That brings us to problem number 16. Okay, clear that out. Okay, this is number 16. Okay, I'm on page 120. And what they want us to do in this one is they give us all the information. They want us to sketch a general graph that satisfies the conditions they give us. Okay, 1, they tell us f of 0 is equal to f of 2 is equal to 1. 2, they tell us limit as x goes to 2 from the left side, my f of x is equal to positive infinity. Okay, and they tell us limit as x goes to 2 from the right hand side, my f of x is equal to 0. Alright, 3, they tell us limit as x goes to negative 1 from the left hand side, my function is equal to negative infinity. And they also tell us limit as x goes to negative 1 from the right hand side of f of x, this has to go to positive infinity. Alright, 4. Okay, they tell us the limit as x goes to positive infinity of f of x, that means the end behavior, that's equal to 2. And then finally limit as x goes to negative infinity, that's the end behavior to the left, and f of x is equal to positive infinity. Alright, so we have to sketch the graph based on these conditions. So let's start with the first one. Okay, so let's go over here, draw x and y axis. Okay, that's my 0. Okay, that's my x, and that's my y, that's my x. Okay, so when x is 0, then the value of the function is 1, so call that 1, and I get that. And then when x is 2, okay, the value of the function is also 1, and I get that. And that's just that right there. Okay, nothing more than that. Okay, now I have to satisfy the next condition. When I go to 2, okay, from the left hand side, my curve has to go up. So when I go to 2 from the left hand side, there's my 2. Okay, and when I go to 2 from the left hand side, this curve has to shoot up. So that means when I go to 2, this thing is going up like that. So when I go to 2, the curve has to shoot up. Okay, that's what this is. Okay, and then this one says when I go to 2 from the right hand side, okay, that this curve is going to have to go to 0. So that means we have some curve, and I have to put an open circle because otherwise it won't be a function. Okay, and I can draw that. Now I have, when I go to 2, the function here goes to 0, so that's satisfied. Okay, now let's go to number 3. When I go to -1, okay, from the left hand side, call that -1. Okay, when I go to -1, the curve has to go down. So that means I'm going to have a vertical asymptote there. The curve is doing that. I have a vertical asymptote there. Okay, that's satisfied. Now when I go to 1 from the right hand side, okay, that means when I go to -1 from the right hand side, when I come from the right, the curve has to go to positive infinity. So here's my curve, it's going to positive infinity. So there's my vertical asymptote. Alright, so both of these conditions are gone. Now, they give me end behavior. When I go to right, okay, the curve here has to flatten out against 2. That's my horizontal asymptote. So the curve gets bigger and bigger and bigger, and it flattens out against 2. Call that 2. Okay, and there it is. And then the last condition, when I go to -infinity, okay, the curve has to go up. So when I go to the left, the curve has to go up. And there it is. And that satisfies all the conditions right there. Okay, so what I want you to do for the homework, okay, I want you to do 1. This is on page 118, or classwork, make sure for class. Okay, 118, 1 through 19 on. Now, on number 19, if you have a graphing calculator, you can do that. If you don't have a graphing calculator, then you'll have to punch in each value, create a table like they have in the book. Okay, but if you have a graphing calculator, okay, maybe it's a good idea for you to go to the graphing calculator and make your life much easier. Okay, that's it.